Welcome everybody to this second video of the series, based on a plenary lecture delivered at the 9 Particles conference held last October. In the first part of the lecture, we introduce the theoretical foundation of the smoothed particle hydrodynamic and discuss the first fundamental compromise that is required when dealing with free surface flows. In this second part, we move one step forward. We will focus on numerical issues, typical instability of the SPH methods, and on the modern formulation that have been developed over the years to overcome this limitation. As I already mentioned, the history of SPH can really be seen as a high history of compromises. The first major compromise was the relaxation of the original Hamiltonian formulation, which was necessary to make the method practical for complex free surface flows. Now we are focusing on a second key question. Does the numerical scheme need to remain strictly conservative, or we can deliberately relax conservation in order to improve stability and accuracy? This question will guide the discussion in the next slides. In this slide, I briefly recall what I previously referred to as scheme number 4. Here we see the complete SPH system, the continuity equation, the momentum equation, the energy equation, and the particle advection, all coupled through a state equation. On the right hand side of this slide, I summarize the conservation property of this formulation and what I call the first compromise. In order to properly deal with free surface, the SPH system is no longer a canonical Hamiltonian system. This loss of the Hamiltonian structure is the price we pay to make the method applicable to realistic free surface flow problems. Let us now move to a second compromise. This formulation, although formally conservative, may lead to non-physical solutions. In particular, we often observe an artificial transfer of mechanical energy into compressible energy, driven by high-frequency numerical modes. This spurious solution appears especially in weakly compressible flow simulation, where pressure waves and density oscillation can easily dominate the dynamics if they are not properly controlled. Since an example is often worth 1,000 words, let us consider a classical benchmark test case widely adopted in the SPH community and originally introduced by Professor Monaghan. In a two-dimensional framework, we consider a circular drop of an inviscid liquid subjected to a conservative radial force, starting from the initial velocity field shown in this slide. The exact solution of this problem is well known. The drop starts to oscillate periodically, deforming its free surface into elliptical shapes. This video shows the solution obtained with the SPH scheme number 4 using a symplectic time integrator and a small CFL number. The particle colors represent the vorticity. It is important to recall that the exact solution of this problem is irrotational. As you can see, although the first oscillation period is captured correctly, the global motion progressively damped out. At the same time, a chaotic particle motion appears, characterized by a sort of artificial internal turbulence and by high values of vorticity. As a consequence of these dynamics, the mechanical energy decreases over time, while the internal or elastic energy increases. Even though the flow is theoretically inviscid and the total energy should be conserved, an irreversible numerical mechanism takes place. This behavior is not related to the loss of the Hamiltonian structure of the scheme, nor to the specific time integrator that is adopted. Concerning time integration, we should note that when a fourth-order Runge-Kutta scheme is used with a large CFL number, additional error in energy conservation becomes visible. In this case, the error introduced by the time integration is amplified by the highly chaotic small-scale particle motion. On the contrary, mass and momentum remain perfectly conserved, and they are not deteriorated by the time integration scheme. However, by reducing the CFL number, this energy error can be effectively limited, independently by the particular time integration scheme that is adopted. If we now increase the number of particles, the unphysical particle motion are progressively reduced. From a theoretical point of view, SPH is a consistent method, and therefore it converges toward the correct solution. However, this convergence comes at the price of very large and often impractical computational costs. The solution is to introduce a numerical diffusive term in the continuity equation, which is able to remove the instability we observed before. By adding this term, we can see that the compressible energy now matches the analytical solution. It becomes periodic, without any accumulation over time. The mechanical energy still decreases, but in this case the dissipation is directly linked to the numerical diffusion term that we have introduced. Once again, by increasing the number of particles, the effect of the numerical diffusion are progressively reduced, so the consistency of the method is preserved. As a final remark, this stabilization allows us to safely use a fourth-order Runge-Kutta scheme even with a relatively large CFL number. This animation shows the solution obtained with the new SPH scheme that we called delta SPH, where delta denotes the numerical diffusion term that has been introduced. As you can see, the solution is now well behaved. The spurious vorticity that was present before is completely removed. Once again, this plot shows the convergence of the internal energy as the number of particles increases. When numerical diffusion is introduced in the continuity equation through the delta term, the unphysical high-frequency chaotic motion of the particles is effectively removed. As a consequence, the role of the time integration scheme becomes much less critical, and we can safely use a fourth-order Runge-Kutta method with the large CFL numbers, significantly reducing the computational cost. In the past, some confusion existed on this point, and a sort of myth developed around the dominant role of the time integrator. What these results show is that once the underlying numerical instability is properly controlled, the time integrator is not longer the limiting factor. This conclusion is also clearly stated in the annual review article mentioned on this slide by Professor Springel. This slide summarizes the main advantages and drawbacks of the delta SPH model. The advantages are essentially the same as those of standard SPH formulations, in particular in terms of flexibility and applicability to free surface flows. Concerning the drawbacks, delta SPH, like most SPH schemes developed for free surface flow, is a non-canonical Hamiltonian model. In order to remove the high-frequency numerical modes, an artificial dissipation mechanism is required. That is what I called the second compromise. Moreover, by modifying the continuity equation, adding the numerical diffusivity, we introduce errors in the link between particle position and the geometric volume they represent. Finally, all the SPH scheme discussed so far suffer from tensile instability, which, as I will show later, can significantly limit the applicability of the method in many engineering problems. I will show that in order to remove this instability, other two compromises are needed. The first limitation we address is related to the growth of particle disorder during the simulation. This slide shows a typical benchmark problem used to highlight this issue, namely the Taylor-Green vortex. We consider 4 vortices in a biperiodic domain. As you can see, due to the particle motion, the point distribution progressively becomes irregular. A possible solution of this problem is the use of particle shifting. This consists in a correction applied to particle advection, which help maintaining a more regular spatial distribution of the particles. In this work, published about 12 years ago, we measured the interpolation error of SPH operator inducing by particle disorder. Since particle disorder for the Taylor-Green vortex evolved dynamically in time, as particles rearrange during the simulation, their error also changes in time. In particular, for this example, you see that after reaching a peak, the interpolation error starts to decrease. If we want to avoid this kind of dynamic behavior and keep the interpolation error within prescribed thresholds, we need to modify the particle advection by introducing a particle shifting technique. The first idea was proposed by Professor Monaghan in 1989. However, a more effective algorithm was introduced in 2009 by Nestor and co-authors. This approach was then further developed by other colleagues in the following years. Starting in 2017, also within our group, Pengransun led a research activity focused on the consistent implementation of the particle shifting technique within the delta SPH framework. It was already clear at that time that, in order to ensure consistency, the shifting velocity added to the particle advection must decrease in magnitude as the spatial resolution of the particles is increased. Further proof of this aspect was provided about 4 years ago by other colleagues. In this slide, you can see, for example, how the particle shifting technique is able to rearrange the particle distribution in the case for an impinging water jet against a solid surface. The plot on the right shows how the magnitude of the shifting velocity decreases as the spatial resolution is increased. Besides its consistency, there is still an important theoretical aspect to be addressed, related to the modification of particle advection and to how it influences the conservation property of SPH. A first important aspect arises when considering free surface flows. In order to satisfy the kinematic boundary condition at the free surface, the shifting velocity must be modified. In particular, it can only have a tangential component along the free surface, as emphasized by Dr. Caillère and co-authors. Secondly, as remarked in these two articles, when particle advection is modified, the formulation is no longer strictly Lagrangian. As a consequence, an arbitrary Lagrangian Eulerian framework should be adopted in order to consistently modify the governing equation. If we explicitly account for the shifting velocity, we can assume or enforce that particle masses remain constant during the time evolution. This leads to what we refer to as a quasi-Lagrangian approach. Within this framework, it is possible to derive a new SPH scheme in which mass and linear momentum are conserved. However, the conservation of angular momentum is lost, and the energy balance is directly affected by the shifting velocity. In some cases, this additional contribution can even become antidissipative. This slide reports the advantages and drawbacks of the quasi-Lagrangian SPH models. The tensile instability is still present when using particle shifting. Indeed, the latter can only partially compensate for this instability. To remove it, we need the last compromise. This is reported in the work by Dr. Pengransun and co-authors. Here, the flow past an airfoil is considered. It is well known that the upper surface of the wing, the so-called suction side, is characterized by negative pressure relative to the far field. When simulating this type of flow with SPH, numerical cavitation can appear due to the tensile instability. As a possible solution is to modify the SPH pressure force interaction to prevent this unphysical effect. To remove tensile instability, we need to modify the pressure formula by changing its sign when the pressure becomes negative inside the flow. It is important to emphasize that this approach only works if particle shifting is also applied. However, modifying the pressure in this way came at a cost. It breaks the conservation of linear momentum. Let's now talk about modern SPH models. I will discuss in this presentation the one developed within my group in collaboration with other colleagues. The first one is the rod SPH. From the governing equation, we can see that the shifting velocity is included, similar to the quasi-Lagrangian SPH model discussed before, namely the consistent delta plus SPH model. However, the scheme is stabilizing using Riemann solver, providing a more general framework compared to the delta SPH. Tensile stability is addressed by modifying the pressure force. Inside the fluid, a second-order formulation is applied, while near the free surface, the classical standard SPH pressure formula is retained. This is the delta-less SPH scheme, which is very similar to the rod SPH. The main difference is that, in addition to the standard numerical diffusion, it also includes contribution from a subgrid model, which is necessary to perform large eddy simulations. In this slide, I summarize the advantages and drawbacks of these modern SPH models. As you can see, mass conservation is the only conservation property that is still strictly preserved. In practice, standard SPH is used only in the free surface region. This allows the automatic enforcement of both free surface boundary conditions. Pressure and tensile stability are effectively removed, which is crucial for applying SPH to a wide range of engineering problems. The accuracy of the method is also improved. Particle shifting ensures a regular particle distribution in space, while the second-order pressure formula enhances the accuracy of the pressure gradient. This is especially important in complex free surface flow, such as during liquid impact events. We can now move to the final topic of this presentation, focusing on how these modern SPH schemes can be applied to emerging and highly challenging flow problems. The first application is related to the European project SLOW-D, Sloshing Wind Dynamics, which focuses on the sloshing dynamic of the fuel tank inside an aircraft wing. When an aircraft encounters a gust of wind, the wing can start to vibrate. The damping of this vibration is strongly influenced by the sloshing of the fuel. This effect can be significant and therefore must be carefully taken into account in the aircraft design. During the project, several experimental campaigns were carried out. This ranged from a scaled wing model to a simplified wing configuration consisting of a metal beam with water tanks mounted on the top used to reproduce the effect of the fuel sloshing. At the most simplified level, a single liquid tank was forced to move vertically using a system of springs. Here you can see the details of this last simplified configuration. From the time history of the acceleration, we can observe that values close to 10g are reached, which are representative of the accelerations that can occur inside a vibrating aircraft wing at full scale. As a result of such strong vertical acceleration, highly violent sloshing flow develops, which is very challenging to reproduce numerically. If we use a conservative SPH scheme, tensile stability causes the flow to detach from the bottom of the tank during the first oscillation. This leads to a completely incorrect physical behavior. Indeed, after the flow detached from the bottom, a violent impact of the liquid on the roof of the tank occurs, leading to an overestimation of the sloshing dissipation. As shown in the plot on the right, this dynamics is repeated in subsequent cycle, reproducing an unphysical step-like behavior in the prediction of the sloshing dissipation. Conversely, when the delta-less SPH model is used, the correct physical behavior is recovered. In this slide, you can see how this model is able to eliminate tensile instability both in 2 and 3-dimensional simulations, while correctly reproducing the formation of liquid jets impinging on the roof of the tank. This slide shows an animation of the simulation. We can observe the first liquid impact on the roof of the tank during the initial downward motion, followed by highly violent sloshing regime, which we refer to as the shaking regime, characterized by intense sloshing dissipation. In this video, the SPH particles are rendered in a way that provides a more realistic visualization. On the right-hand side of the screen, the arrow indicates the vertical position of the tank. As time progresses, the tank motion gradually decays due to the mechanical friction and the sloshing dissipation. Towards the end of the simulation, the tank motion becomes very small, and the flow transitions to a more regular sloshing regime, with fewer and weaker liquid impacts on the roof. Here is another snapshot taken just after the first liquid impact on the roof of the tank. On the right-hand side of the slide, the two-dimensional case is reported and the colors represent the vorticity of the field. Indeed, during the shaking regime, the continuous fragmentation and reconnection of the liquid interface lead to complex turbulent flows both in two and three-dimensional frameworks. In particular, in three-dimensional case shown in this slide, you can observe the formation of complex vortex tube structures. From the experiments, it was possible to evaluate the sloshing dissipation by measuring the hydrodynamical forces and the tank motion. This global quantity can therefore be used to validate the SPH model that we adopt. In this slide, the measured sloshing dissipation in time is shown in the left plot with the black curve, while the colored curves correspond to SPH simulation performed at different spatial resolution, so increasing the number of particles. The plot on the right shows the convergence of the final SPH predicted dissipation towards the experimental value, with a convergence rate between 1 and 2. This result is quite remarkable, especially considering that, for computational cost reasons, the higher phase was not included in the simulation, even though it does not seem to play a dominant role in the evaluation of the sloshing dissipation. The last project in which we applied modern SPH scheme is HASTA, another European research project. This project focuses on the sloshing of liquid hydrogen inside the tank located in the aircraft fuselage. Compared to the previous case, this problem is even more demanding because it involves cryogenic sloshing flows, where heat transfer and thermal effects can also play a significant role. For this project, we develop a dedicated SPH scheme that we call Delta Star SPH. In practice, this is an extension of the delta-less SPH in which the temperature equation is also included and coupled with the momentum equation through a buoyancy-driven force. A first validation of the new scheme was carried out on natural convection problems. We consider a tank whose walls are at a much higher temperature than the liquid in its initial state, and we assume that the gas phase remains isothermal at initial low temperature of the liquid. The classical dimensionless number governing this type of problem are the Prandtl number and the Grashof number, or equivalently the Rayleigh number. The Froude number is directly linked to the temperature difference between the tank wall and the gas. When the Froude number remains sufficiently small, the free surface stays almost flat and only weakly disturbed. In this slide, the video shows a case with a moderate Rayleigh number around 500,000 and a small Froude number 0.082. The colors indicate the temperature field. You can observe the formation of hot currents, especially along the lateral walls of the tank, which rise upward and are then cooled at the free surface, generating downward cold currents. As a result, Rayleigh-Bénard convection cells develop, and, as expected from the literature, they are in an unstable regime. This slide shows a comparison at the initial stage of the flow between delta star SPH and OpenFOAM, which is a well-known finite volume solver. Both solvers capture the formation of characteristic mushroom-shaped plum in the flow. But is it really necessary to use a new SPH scheme for this kind of problems? Or could we rely on a more traditional SPH formulation instead? From our experience, the answer is yes, modern SPH schemes are necessary. For example, in this slide you can see the solution obtained with the delta SPH and the delta plus SPH. Both of these solvers fail to reproduce the correct behavior. The delta SPH scheme completely dumps the flow motion, while delta plus SPH, on the contrary, greatly amplify it. Looking at the time histories of the average temperature and kinetic energy, we can see that the delta star SPH, the orange curves, are in a good agreement with OpenFOAM black dots. In contrast, the other two SPH solvers, green and red curves, produce completely unphysical solution. In particular, delta SPH tends to dump the motion of the particle, while delta plus tends to largely amplify the particle motions. Summarizing, it seems that the combination of the particle shifting technique together to the second order pressure gradient are necessary to get good comparison with OpenFOAM. Since we want to simulate liquid hydrogen, we need to tackle much higher Rayleigh number regimes. This is second test case where Rayleigh number is about 2.6 billion, inducing a completely turbulent regime. Here is the comparison of the temperature field at the same instant between delta star SPH, OpenFOAM and star CCM+, which is another famous finite volume solver. In this slide we can see the video of this second test case. Similar to the first case I showed, also in this case the thermal boundary layer is unstable, but this time is characterized by much smaller vertical structure. The heating process appears much slower since the upward and the downward current are thinner and more irregular because of the turbulent regime. It follows that their flux are less intense than the previous one. Here we compare the time history of the average temperature and the kinetic energy obtained with the three different solvers. Considering the complexity of the simulated flow, the delta star SPH results show very good agreement with the finite volume solvers. This study was carried out in collaboration with ENEA and the Polytechnic University of Madrid, which provide the finite volume reference solution for these natural convection cases. Finally, I would like to show a couple of examples of cryogenic sloshing. In this case, the liquid is cold. The tank walls are also cold, while the vapor phase is at higher temperature, which is the typical condition for the hydrogen aircraft tanks. If the liquid undergoes only a slight motion, the result is a simple thermal stratification of the liquid. Conversely, when the tank motion is close to a resonant condition, the gas is able to heat the liquid much more rapidly. As shown in this video, the violent liquid motion leads to the formation of thin jets and to the fragmentation into droplets. Both the jets and the droplet are heated very quickly, and when they impact the underlying liquid and re-enter the bulk, they act as an efficient mechanism for heat transfer. In this snapshot we can clearly see the jet and the droplets, which are at higher temperature than the underlying liquid. The main heating mechanism is therefore driven by the strong deformation of the free surface by its fragmentation and by the repeated entry of jet and droplets into the liquid bulk, as further illustrated in this slide. To summarize, by looking at the time history of the average temperature, we can clearly see how the heating process is completely different in these two oscillation regimes of the tank. Slightly motion, stratification of the temperature, and the increase of the average temperature is very limited, while on the contrary, when the motion become are close to a resonant regime, you see that when the free surfaces start to largely deform, the heating process become very energetic. With this final slide, I conclude my presentation, and I hope I have provided a clear and an updated overview of the smoothed particle hydrodynamics method and of its recent development for the simulation of violent free surface flow. Thank you very much for your attention.